Hello, and welcome to the AAE 450 EAPS 391 Senior Design presentation. This presentation is the culmination of a semester-long design effort led by a 56-person team consisting of aerospace engineers and planetary scientists. First, we'll start off by describing the scope of Project Future Mars. The goal of this project is to analyze what a steady-state, self-sustaining city on Mars would look like in the future. By steady state, we mean that there is no resupply from Earth whatsoever, so all of the systems on the Martian surface must be maintained, manufactured, and replaced with materials that come from anywhere but Earth. We were given other various constraints by our customer as well as our professors when designing the city. These requirements are given at the top of the slide. So for example, the city also has to be a pressurized environment inside of a Martian lava tube that can support 10,000 people. And the humans that live in the city or traverse across the Martian surface must have their radiation exposure mitigated to Earth sea level equivalent per year. Lastly, our communications infrastructure must provide constant two-way HD communication between Earth and Mars. The picture on the bottom of the slide depicts the overall picture of the various systems we have designed to support 10,000 people on Mars. We have a manufacturing facility, a city, resource extraction equipment, a vehicle assembly building, a fleet of launch vehicles, as well as a communications infrastructure and an interplanetary transport system. It's also important to understand the context of this design challenge with respect to the rest of the aerospace industry. Although our mission is ambitious, there have been many well-respected leaders that have come before us that have envisioned greater things, such as Gerard O'Neill and the O'Neill cylinders, which are orbiting platforms that are 8 kilometers in diameter and upwards of 30 kilometers long, with hang gliders and waterfalls. And more contemporary examples, such as Robert Zubrin and Elon Musk, with grand visions of terraforming Mars and creating a 1 million person colony by 2100. We choose to draw inspiration from these permanent space societies, but chose to create a more realistic approach to how we can sustain human life off of Earth. Now we're going to give a little background on what a lava tube is exactly, since our city must be located inside of one. Lava tubes on Mars were formed many years ago when the planet was still believed to be geologically active. Essentially what would happen is that lava flows would continuously cool and leave behind these snake-like, hardened tunnels underground. The picture on the bottom of the slide is an example of a lava tube here on Earth. There are a couple of ways lava tubes can be identified on the Moon or the surface of Mars, via a skylight entrance or a collapsed trench. A skylight entrance, depicted in the figure on the left of the slide, is when the ground collapses in and leaves an open hole where you can see into the bottom of the lava tube. The second way a lava tube can be identified is via a collapsed trench, where a large portion of these lava tubes would collapse in and allow us to see into the side of a lava tube. This is actually how our lava tube was identified. The picture on the right shows where our city is located, and the holes you see on the surface are the collapsed trench sections. These lava tubes span great lengths, as seen on this image, which is almost 20 kilometers long, and are much larger on Mars due to the lower gravity. The benefit of living inside of these lava tubes is that it provides a free shelter to protect from various hazards such as dust storms, radiation, and micrometeoroid impacts. Now we'll talk about what our city looks like inside of this lava tube. This shows the entrance into our lava tube. And if you remove all of the regolith, you see the various aspects that are hidden underground. We have a manufacturing facility, a city, and a collection of reactors that power almost every piece of machinery on the Martian surface. And here is a short rendition of how we enter our lava tube. We travel down the slope we have created, and we enter a pressure bulkhead via an airlock. And now we're in the city. This serves as a reminder that our lava tube is actually located underneath about 50 meters of regolith. We estimate our city section of our lava tube to be about 1.5 kilometers long and 300 meters wide and 100 meters tall. And this depicts what is located inside of our 10,000 person city. Although this semi-ellipse structure is convenient for radiation shielding, it is actually not safe enough for our citizens without reinforcing the rock. We've implemented a concrete layer with rock bolts to ensure the lava tube does not collapse. We have also implemented trusses toward the tallest points in our lava tube to ensure the top is properly supported. There are also multiple other amenities, such as gyms, hospitals, and our food distribution centers. We grow all of the food needed to sustain our citizens underneath the city in our aeroponics buildings. Next, we'll talk about what our food production system looks like. Here is a short clip on what a module in our aeroponic building looks like. When crops are grown aeroponically, the roots hang down and mist with the proper balance of nutrients is sprayed onto the root systems. We grow a variety of crops to ensure our citizens have a balanced and varied diet. Some of the examples are depicted at the top of the slide, such as strawberries, oats, broccoli, and crickets. Crickets are actually a great source of protein and are rich in B12, which is key for a healthy lifestyle. Now, in order to keep our city and crops surviving, we must collect a variety of resources that can help sustain our city. In order to collect the resources that allow us to maintain our city and its population, we must leave the comfort of our lava tube and venture onto the surface of Mars. As mentioned before, our city is located by the Mahuro Canyon near Hellas Basin, which is displayed on the map. Next, we can see some of the locations we traveled to in order to collect these resources, including Gale Crater and Shalbatana Vallis. In order to reach all of these resource extraction sites, a rail line system was installed. This rail system proved to be the best option given that these sites are fairly permanent and that the rail cars could carry much more resources with less power than compared to suborbital hoppers and rovers. Relative to our city, the closest resource extraction site is our water extraction site, which is about 200 kilometers away, and the furthest ones are to collect the thorium that we use to power our reactors, which is about 8,000 kilometers, and the copper that we need for our electronics, which is just over 8,200 kilometers away. It should be noted that the reason that some of our extraction sites are so far from our city is due to the fact that we decided to only select resource sites for which we had data about the regolith composition, which were provided by previous Martian exploration missions such as Curiosity or Spirit. It is likely that there are sites closer to our city where we can find those key resources, but this would only simplify our design. One of the ways that we collect resources is through our water processing system. The system is placed on top of an underground glacier in Hellas Basin and uses a Rodriguez well to extract and collect the water from this glacier. The way that this process works is by injecting hot steam into the glacier, which melts the ice and creates a well of liquid water. This liquid water is then extracted and sent to our city through a piping system. Conveniently for us, this location is at a higher elevation than our city, allowing us to use gravity and let the water run down to us. Due to this downward slope, we have also installed turbines along the pipeline that collect energy from the water, which generates enough power to sustain the entire water processing system. Another way we collect resources is by collecting regolith at specific locations. To do this, we use a dragline excavator that digs through the Martian surface and collects regolith into a pile. The regolith is then moved from the pile into a dump truck through an intermediate excavator. This dump truck then moves towards the rail line along a charging road that maintains the dump truck's battery. Once at the rail line, the dump truck deposits the regolith into a crushing facility that grinds the regolith down to a finer powder, and it is then moved onto the resource rail car where it will be transported to our manufacturing facilities. In order to collect more rare metals, like gold or silver, a series of dump trucks were modified to have giant magnets underneath them so that they can scour around the surface near these extraction sites to collect iron meteorites that contain these rare metals. All of these resource extraction machinery are teleoperated from the city to provide these semi-autonomous extraction sites. Additionally, both the rail car and extraction equipment are powered from the city grid. The rail cars receive their power through power lines that run through the rail line, and resource extraction equipment receive their power through power lines that run alongside the rail lines. The manufacturing modules consist of factories that span 900 meters in length with the same cross-section profile as the city. Once the collected regolith makes it back to the manufacturing modules on the resource rail cars, it is broken down into its raw elements. Later, these raw materials can be transformed into more useful materials like steel or aluminum alloys. Another important system that is housed in our manufacturing modules is the atmospheric processing system. This system collects 17 tons of Martian atmosphere per day. Through processes like fractional distillation, Sabatier reaction, and water electrolysis, the atmosphere is converted into argon, methane, nitrogen, oxygen, carbon dioxide, and carbon monoxide, which are used to maintain the atmosphere in our modules and as rocket propellant. Additionally, some of these gases are also used in our aeroponics system as well as manufacturing processes. Finally, materials are machined and assembled into finalized systems. These facilities are capable of producing anything from aeroponics nozzles to satellites, from computers to rocket parts. The only systems that are not fully assembled here are our rockets, since they would take up too much space. For that, we have the Vehicle Assembly Building. This Vehicle Assembly Building, which is home to our fleet of rockets, has the capability of housing 2 separate rockets at a time. Rockets are rolled out of the Vehicle Assembly Building on the crawler vehicle and erected on the launch pad through a system of winches, where it will be prepared for launch. These launch vehicles are in charge of launching exploratory science missions, maintaining the satellites in our communication fleet, and taking up to 50 tourists at a time to our interplanetary transport system. Here we have our taxi vehicle docking with our interplanetary transport system, or a powered cycler. A cycler is a spacecraft that travels on a set schedule between Earth and Mars by taking advantage of repeated orbital geometry, effectively acting as a bus. The cycler takes 2 Earth-Mars synodic periods between Mars flybys. To reduce this time, we decided to place 2 cyclers at opposite ends of their trajectory, reducing it to every 2 1/7 years, with travel times between Earth and Mars lasting about 310 days. Displayed here is a more technical plot of our cycler's trajectory. The red line displays the distance between Mars and the Sun, while the blue line displays the distance between Earth and the Sun as time passes. The reason why these change is because of the orbits of these planets are not perfect circles, with Mars's orbit being more eccentric. The green line on the maps represents the cycler's trajectory when there are people on board, and the black line represents the cycler's trajectory when no one is on board. The pattern displayed on the plot repeats almost identically about every 30 years, which is why we can use this analysis for the time period we're considering. This is what our cycler vehicle looks like. Travelers will live on the outside ring of the spoked wheel, which continuously rotates to provide artificial gravity of 0.1 g. The cycler also has Hall effect thrusters in order to have a lower hyperbolic velocity, which allows for a smoother and safer rendezvous with the taxi vehicle. As seen in the animation before, the taxi vehicle connects with the rest of the cycler on one end that does not spin in order to further reduce the risks of this rendezvous maneuver. Finally, our cycler has 2 communication antennas that transmit signals for the Mars-Earth High Data Link communication network. This communications network is used to satisfy the constraint of continuous HD communication between Earth and Mars. A constellation of 3 geostationary satellites around Earth and 3 aerostationary satellites around Mars were set up. The Martian constellation sends data to one of the 2 cyclers, which then relays the data to Earth and vice versa. Every 15 years or so, a solar conjunction event happens. This means that the Sun, Earth, Mars, and both cyclers are in a line, which prevents communication since the communication signals cannot travel through the Sun. In order to mitigate this, a separate communication satellite was placed on an orbit similar to that of Mars but shifted by 8 degrees. This relay satellite can be used in the solar conjunction event as it acts as a single relay point between Earth and Mars during that period. Additionally, we also installed the Martian Communications Network, which consists of 4 satellites in a DREAM configuration that orbit Mars. These satellites have the capability of covering the entire surface of Mars at once. They can also communicate with one another to relay data that can be downlinked to the only ground station, which is located in the city. The main purpose for this communications network is to act as a relay between scientists and scientific rovers that are scattered throughout the surface conducting a plethora of research. The constellation sends instructions to these rovers and relays their collected data by communicating with up to 35 rovers at any given time. As we just mentioned, there are multiple research rovers that are roaming the surface of Mars to answer some of the open questions that we have about the red planet. The rovers are a part of a collection of scientific instruments that will address some of these open questions. The rovers are used to collect various samples to investigate the composition of Mars's crust as well as biosignatures. We have also implemented an X-ray and optical telescope to see farther than we've ever seen before. The advantage of looking at our galaxy from Mars's surface rather than from Earth's is that Mars does not have an ozone layer to inhibit these cosmic views. We have also designed landers to visit both of Mars's moons, Phobos and Deimos. These landers hope to solve the question of the origin of the moons, whether they are coalesced equatorial dust or captured asteroids, or even have another origin. Lastly, we have implemented seismometers across the Martian surface which serve to map the interior of Mars. These hope to unveil whether or not Mars has a continuous crust, a molten core, or ongoing seismic activity. By implementing this fleet of scientific missions, we hope to solve the key questions we still have about the red planet. We'd like to wrap up with the lessons that we've learned or key takeaways from this study. First, we discovered that water is relatively easy to find and easy to get. This proved to be very useful considering our colony could not survive without a large continuous water source. Next, we found that nitrogen is vital to the survival of our city and our crops. Crops must intake nitrates in order to stay healthy and produce significant yields. It's also important to have nitrogen in our city's atmosphere because it is unsafe to have a completely oxygen-rich atmosphere. One of the most interesting findings from this study was that the rail system was the best method for transporting goods and people across the surface of Mars. This method was compared to suborbital hoppers as well as rovers, but the rail system proved to be far more efficient in terms of resources delivered and power required. Another interesting finding was that despite Mars's cold atmosphere, heating the city was not the problem. Cooling it was. We had to develop ways to utilize the excess heat from the factories, from the human bodies, and from the intense lighting inside of our aeroponics building. One of the more challenging aspects of this design was that we discovered molybdenum was very rare but necessary for both manufacturing processes and human consumption. All of our resource extraction requirements are met with a factor of safety of 1.2, except for molybdenum, which is right on the cusp of being met. Although the lava tubes are pre-existing, we found that it's not just as simple as building a city inside the lava tube, because these structures are not stable or safe enough. We had to implement significant reinforcements to ensure the citizens of the city are safe from collapse. Lastly, we were given the difficult constraint of mitigating radiation levels on the equivalent of sea level on Earth per year. This constraint affected the design in multiple ways, because Mars sees large amounts of radiation which would in turn severely impact the amount of time humans can spend on the surface maintaining or repairing systems. We'd like to acknowledge the 56 people behind this design project that have contributed to its success. These seniors worked on an interdisciplinary team from multiple different disciplines such as CAD, power and thermal systems, human factors, mission design, and more. Thank you for listening.